The picture matching application is application for measuring distance between two pictures as vectors. On this slide is shown a call graph that describes main data flow in this application coming from JPEG file, and until to normalized distance value between two pictures. First step in this application is reading a picture and after that transforming picture format from a standard picture format like JPEG, PNG or GIF to bitmap format. After that we have three metrics for making image signature. First metric serves for getting pixel value from GD image and also corresponding red, green and blue value. Second metric is serves for determining average level from neighboring points in view, including grid point. By default, that is 9 points, and for this serves soft edge the level function. And third metric is metric for determining average level from points within determined square, and for that serves puzzle get average level function. All three metrics result in average levels matrix. By default 81 points. Finally, by comparing each value with its neighbors that are 8 points, we get image signature, so-called D vector, and after that we transform D vector into C vector, and with vector subtraction and vector Euclidean length functions we get normalized distance between two pictures. For understanding scalability on picture size level, it is crucial to understand that signature consists of number of neighbors, that is 8 times square of lambda points, where lambda is number of points in each axis. For each such point is needed square of p calculations for average level, where p is minimum between width and height, divided by lambda plus 1 and with the p ratio. For such point is needed 9 calculations for soft edge the level, and in addition for getting a view from GD image is needed with the times height calculations for pixel values, and for view auto cropping is needed double with the times height operations for each axis separately, and eventually almost starting matrix size for getting resulting view. Scalability regarding number of pictures. I started with one assumption that only small number of pictures are similar or close resemblance to the reference picture, because we have a large number of pictures in start, about 10,000 pictures, and in that case most number of pictures will exit program after second if program, after second if command, and only small number of pictures will enter inner loop, and yet smaller number of pictures will pass through loop all 10 times, because either the current picture will find its place among top 10 pictures earlier, before 10th place, or until then all top 10 places have not been taken yet. Under this assumption, execution time is dominated by the other different pictures that are above matching threshold, and execution time is a linear function of number of pictures. That is shown in this code, where most pictures will exit outer loop after second if command, and only small number of pictures will pass into inner loop. I made profiles of execution of this application for different picture sizes, starting from 0.5 megapixels to 20 megapixels, in order to get distribution of time over different functions in program. I marked bottleneck functions, that are functions with most participation time in total execution time. Those functions are, among others, functions for reading picture files and transforming picture files from standard types to bitmap. Also, that are puzzle fill d vector from a file, and puzzle fill average values. Also, puzzle autocrop view function takes a lot of time in total execution time, and those four functions are candidates for parallelizing. Another function important for this profiling is GD image getTrueColorPixel for getting pixel value from picture in order to set our view that is representation of picture. All pictures of interest showed their behavior on the previous charts. Question of interest is why something to parallelize and why something not to parallelize. Certainly not to parallelize loops that can create data race conditions that is shown on this slide with the puzzle autocrop axis function, where one variable chunk contrast is used for sum of contrast across entire matrix, and in that case different loop iterations are not independent, and in this case parallelization should be avoided. First candidate for parallelizing is puzzle getView from GDImage function, because the loop iterations are independent for using Silk4. Only coordinates x and y determine the loop iteration. Second candidate for parallelizing is puzzle fill average levels function, where the loop iterations are also independent for using Silk4, and the loop iterations are only determined by coordinates Lx and then y, and I will replace average level variable with the current matrix value. Third candidate is puzzle vector subtraction function, but this function is not so important. And fourth candidate is puzzle autocrop view, because there is possibility for a recursion when cropping original matrix, because we can divide space between original and resulting matrix into three parts in order to get three parallel for loops, and then each recursion will call three parallel loops, and after that next recursion call. But this function is dominated by the execution time of sequential puzzle autoprop axis function, and in this case I will not achieve considerable savings in execution time.